Hi everyone, welcome back to another episode of sound design for video games. What you're looking at here is the complete car engine audio system Metasound. Now it's quite a large Metasound, which is why today what we're going to be doing is we're going to be going over prototyping. Prototyping is basically the planning process where you make sure everything's going to be working properly. So you can see this big Metasound. This is what I started with. And we're going to be going over this, and basically if you understand this smaller scale Metasound, you'll understand this larger scale Metasound for the next episode. So for those of you that are particularly new to Unreal Engine, this is going to be a really important episode to get your head around this. Now the first part of the planning process is about identifying problems and then proposing solutions. So for the car engine system, the first problem that we have, and I'm just going to remove myself. The first problem that we have is excessive pitch shifting. So you can see here I've put destroys audio quality. So if you pitch shift too much, obviously that will end up destroying the quality of the audio, especially if you're using a real car engine audio. The solution I've got here is we'll use multiple samples of audio at desired pitches, and then we're going to crossfade between them, and that's going to allow us to limit how much pitch shifting is required. Now problem 2, we're going to be using the vehicle rotation speed. That's essentially the revs, the rev of the engine, and we're going to be using that number to set the pitch shift. The problem is our vehicle rotation speed is in thousands, and the pitch shifter in Unreal Engine is obviously in semitones. So you're using a number that is in thousands, which is too large because obviously we're just dealing with 1 to 12, essentially. The solution here is very simple. You just multiply that number by 0.001, which takes it from thousands to ones. Now for problem 3, essentially if 1000 RPM equals 1 due to this multiplier here, and then 2000 RPM equals 2, again due to this multiplier here, then the issue we have is that the incrementation of pitch shift will be wrong, because we're going to be pitch shifting 1 for when it's at 1000 RPM and 2 for when it's at 2000 RPM. But 1000 to 2000 is an octave, which means what we need is 12, because 12 semitones is an octave. So what we need to do is we need to multiply these values by 6, okay, because that's going to take the 2, 6 times 2 equals 12, therefore we have our semitone incrementation correct then. We're getting an entire octave of pitch shifting. Now for problem 4, the issue we have is that the pitch shift that we're doing here is not going to be correct for all of the different ranges. So to give an example, 1000 RPM to 2000 RPM is an entire octave, but 2000 RPM to 3000 RPM is half an octave, and that's even less with 3000 to 4000 RPM. So the amount of pitch shift we're needing to get from one range to another range when we are crossfading between all these different audio recordings is continuously getting smaller and smaller. So what we need to do is we need to use a multiplier after this to account for the fact we need less pitch shift. So the formula I have here is essentially it's the higher RPM divided by the lower RPM minus 1. So to show you that with the calculator, let's say we want 2000 RPM to 3000 RPM. So 3000 divided by 2000 minus 1 gives us 0.5. So that's essentially a multiplier that is allowing us to say we need half of what this is saying. And then if I say then, what is it, high of it divided by lower, okay, 4000 divided by 3000, then minus 1. That's going to give us 0.33, and you can keep going with that. So you can go 5000 divided by 4000, which is going to be our top RPM range for this card. The card does go up to 7000, but I find that this is all we needed to do. -1, that's giving us 0.25. So with all this taken into account, we now have the information to make this system work correctly. Another thing we should be thinking about is the interconnectivity of all of the systems. Now, in this instance, we have the engine rotation speed, which then influences the way this Metasound works. But with other circumstances, what you might have is almost like a triangle or a quad system, where essentially you have multiple systems which are interconnected. Now, in that situation, this is where your coding architecture starts to come in, where you're starting to think about, if I do this, how is it going to influence the other things that is then connected to? Now, in this instance, it is a very simple thing. It's one thing influencing another, but just because this video is about prototyping, I wanted to make the point that you should also be thinking about that idea of interconnectivity and where things can go wrong when you've got maybe 3 or 4 things which are all connected together. Let's go over our prototype for the engine audio system. So there's a few things this needs to do. The first thing is we have our test oscillators, which are essentially outputting a sawtooth wave, a sine wave and a square wave, so that we can easily hear that the system is working correctly. Then what we have is a pitch shift area. We have these nodes here, they're called a delay pitch shift node, and what's really nice about this node is that it essentially pitch shifts without changing the length of the audio, so it doesn't shorten or lengthen the audio, it pitch shifts a different way. Attached to the delay pitch shift node are these graph inputs. You simply drag off here, go to promote to graph inputs, as we've been through before. And these could all be the same graph input. At the moment it says 0 freak, 1 freak and 2 freak, that's how they're named. But they could all be the same graph input. I didn't realise this when I was prototyping. Then what we have here, coming out of these ones, is the little bit of maths that we were talking about when we were going through this section here, where we were saying, oh, we need to add these multipliers to make it correct. So we've got this multiplier and this multiplier to essentially make sure that what comes into these delay pitch shifts are correct. And we're getting the correct pitch shift for each of these sounds. Then once we've got the pitch shifting correct, what we then need is the crossfade part of the system. So when the engine rotation speed is low, what we want to hear is the sawtooth wave. So we get this little graph input here, which comes up. When the engine rotation speed goes up a little bit, we're going to go from the sawtooth wave to the sine wave. That's going to automatically be set so that this volume goes to 0 and this volume goes to 1. And then when we get even higher, what's going to happen is this one's going to get to set to 0 and this one's going to be set to 1. And ultimately we're going to hear sawtooth wave, sine wave, square wave as we get higher. And then the mixer's going to take care of that and make sure that we're hearing the correct one, basically. And then coming out of here, we have a little master volume section, which we didn't really need. You could just do that over here. So I've set the gain to 0.25 here. We could have just done 0.25, but just out of habit, I did it like this. And then we're into the out mono. Now, most of this is fairly simple, but I do want to go over some bits in a little bit more detail. Firstly, I want to go over the frequency section here and essentially explain why these numbers are the way that they are, just to make sure we're absolutely clear there. Then I want to go over the crossfade section and essentially explain what's going on here before we go into this mono mixer. How are we processing the gains of all these sounds going into the mono mixer? So let's start with the frequency section here, the delay pitch shift section. So obviously we have none here, and the reason we have none for this one is because this is essentially representing our idle sound. So when the vehicle's not moving, we want to hear this sawtooth wave. As soon as the vehicle moves and the engine rotation speed starts to speed up a little bit more, we're going to then crossfade to this sine wave. We will no longer hear the sawtooth wave due to what's happening here, which we'll go over in a moment. Now when we get to this sine wave, we're going to be at a RPM of 1000. So when we get to an RPM of 1000, that's going to trigger an event to make it so that we only hear this sine wave. Now with what we're receiving is an RPM of 1000, what that means is it means that the number that is being driven into this graph input because we're going to be taking the engine rotation speed and using that value to determine what number this should be. So the number we'll be receiving is a value of 1000. That value will be multiplied by 0.001, which will bring it down to a value of 1, meaning that the value we'll receive here is 1. Now we will be pitch shifting 1 when we're already at 100 Hz. So we're already at the correct frequency, so we don't need any pitch shift the moment we crossfade to this, which is why we're doing 1 plus minus 1. You could have said 1 subtract 1. I put plus minus 1 because I'm weird. So 1 plus minus 1 equals 0. 0 times 6 equals 0. So that means we'll be receiving a pitch shift of 0 in the moment that this gets crossfaded in. As the engine rotation speed speeds up, we'll start to receive pitch shift then, and that pitch shift that we'll be receiving due to this multiplier of 6, which we've already been through in the problems solutions section, will then be correct. We'll be receiving the correct pitch shift, which will then bring us to 2000 RPM. Once we're receiving 2000 RPM, we'll be receiving 2 into this graph input, which is why we then plus it by -2. Again, you could have just used the subtract node and then said subtract 2. Then we're multiplying that by 6, then multiplying it by 0.5, and we're multiplying it by 0.5 because the next one would be 2000 RPM to 3000 RPM, which means we need that to be half an octave. So that's why we have this multiplier. So we have the multiplier that gets us into working correctly with semitones, and then after that we have the multiplier that gets it working correctly in terms of the ratios from one range of RPMs to another range of RPMs. So hopefully that makes sense. I've got a little example here. So 1000 to 2000 RPM is multiplied by 6 multiplied by 1, basically meaning the multiplier is exactly the same. From 2000 to 3000 RPM, we have a multiplier of 6 into a multiplier of 0.5, because that would be half an octave. And then from 3000 to 4000, you see our multiplier becomes 0.33, and then it'll become 0.25, and it keeps getting smaller the higher the RPM ranges are. So that is essentially our pitch shifting section. Hopefully that all made sense. If you do have any issues with that, obviously comment, let me know, and I'll try my best to explain it via text. It is, a little bit difficult to explain until you kind of get your head around it. Now for the crossfade section, we're bringing these delay pitch shift nodes into this mono mixer, and then out of the gains we have pretty much the exact same thing happening for each of these. There are 2 parts. First thing we're going into is an interp2, which essentially interpolates slowly from one value to another based on an interpolation time. So you can have it interpolate very quickly, you can have it interpolate very slowly. Now out of this interp2, the first thing we're going to is this multiplier. Let me just set that back to 1 and set this back to 0 because I set that before. So this is a graph input. Once again, you just drag off this, press graph input. You have to name this correctly. It's very important to name correctly at this point. So this says 0 vol, which stands for the volume of our first tone generator. We're setting that to 1, which means we want 100% volume. That's then going into this multiplier where I've set that to 0.5. That's just because I want half the volume, so it's not as loud. So you don't have to worry too much about that. This is just so that we can very quickly control the volume of this overall. That's then going into the interp2. And then what we have here is a float to time converter. So if I drag off this, you can do float to time. You can see you get one of these nodes. And then what we use is a graph input, a float graph input, to essentially tell how quickly we want this interpolate to interpolate. So at 0.25, we're basically saying we want 250 milliseconds of interpolation. So as this changes from 1 to 0, it's going to change to 0 in 250 milliseconds. So that is where the crossfade comes in, where we are essentially crossfading from one thing to another. This is where that comes in. It's due to the interpolation to node, basically. So these are graph inputs. We have 0 CF time, which stands for crossfade time for our first one. Because this is an idle sound, this is the sound of the idle engine, we need a graph input which is specific to that, because we might want the idle sound to crossfade at a different rate to the rest. What you'll notice is for these are both the same graph input, so I can change this, and you can see this one influences this one, and this one influences this one. So they're both exactly the same. I'm going to set that back to 0.5. So what we're saying is, for our idle engine sound, we want that to interpolate over 250 milliseconds. But for all the other engine sounds, we want them to interpolate over half a second. So it's a much smoother interpolation. Now what we need to do is we need to add this Metasound as an audio component inside of the player controlled blueprints. So in our case, I'm going to go to our vehicle. You might be using the sports car pawn. I've created my own little sedan pawn here. And what you need to do is you need to press Control Spacebar. Go and make sure that you have selected the Metasound that you've just created. So in my case, it's ms_demo_engine concept. So once that's selected, it's very simple. You can just go to here. And then the first thing you'll see is audio, and then in brackets, you'll see the name of that Metasound. When you click that, it's then going to add it to this big list of components. You might have a smaller list than me at the minute. So if I go ms_, and then I can look for my demo engine. So if I zoom in here, you can see it's added it there, that little speaker there. Now once that's added, what that is basically going to do is when you press play for play the game, it's going to essentially automatically play this Metasound, and that Metasound is going to play from that speaker inside of the game world. Right, now we're going to go to the event graph, and this is the section of code here where we are essentially communicating with our little prototype Metasound here. So we have a bunch of things that we're doing. Once you've actually got that little thing here, if I go demo, there we go. You can see you can drag this off and add it to here. And then from here, you can drag off a load of things, which will then going to allow you to communicate with this Metasound. So first thing we need is a way of triggering this. And because we are essentially needing to continually check what's happening at a given moment in terms of the engine rotation speed, the only way you can do this is with the event tick. So if I go over to the event tick over here, here's my event tick. Now it would be very messy if I had the event tick directly connected to my audio logic, because I have a bunch of sort of game logic here, which is for the actual functionality of the game and not the audio. So the way I deal with this, just so that we can keep things organized and looking nice and tidy, I use these call functions and custom events. So if I go back over here, what we have is a custom event. You can get that by right clicking and type in custom events. When you add that, you'll get this little red node here. You press F2 and name that something that makes sense, like an engine test sound. And then once you've added that custom event, what you then need to do, you need to call it, because it won't do anything by itself. It needs to be called by something that's firing off an event. So this is where the event tick comes in. If I go over to my event tick all the way over here, and if I right click on here and type in call function, make sure that's correct, call function engine, there we go, engine test sound. So what I'm going to do is I'm going to move this over here, and we'll just temporarily, because this is purely for test purposes, I'll temporarily connect this up. Now what's happening is every single frame, the event tick is firing off through here, and then it's going to our engine test sound, and that is immediately taking those impulses coming from the engine tick over to our engine test sound custom events. And then this is firing off every single frame to these now. So that's essentially how that's working. Now that we've set up the custom event so that we have the execution pulses being sent correctly, let's go through this area of the blueprints. So the first thing you're going to need is this reference here. This is the reference to this Metasound that we've just done, our little prototype Metasound. This reference is going to be driving all of the commands that we're sending to it, right? So what you need to do is go over here, press ms_demo, and you'll see you can just drag and drop this. And from this, you're dragging off, and you're basically getting a load of set float parameters. So if I drag off this and say set float, you have two. I think I usually go for this one. Yeah, that's the correct one. Now, once you've done that, you'll notice that there's a little bit where it says name. Now, this is where it becomes very important that you name your graph inputs exactly in a way that you will always remember and you won't make any mistakes. Because when you put this in here, this is what basically tells this little reference here which graph input we're talking about. So in this instance, we have 0 freak for the frequency of our sawtooth wave, 1 freak for the frequency of our sine wave, and 2 freak for the frequency of our square wave. So you can see here we have the name and convention exactly the same: 0 freak, 1 freak, 2 freak. Now these float parameters are then being driven by this little bit of logic here. So this is a chaos wheeled vehicle movement component. So you can just get that by typing it in. Chaos wheeled movement components, as you can see there. And then from there, we are getting the engine rotation speed. This is the number that is going to be spitting out in thousands. So like 1000 RPM, 2000 RPM, 3000 RPM. We're then multiplying that by 0.001 to bring that down to 1s, 2s, 3s. And then that is then being driven into the float inputs of each of these float parameters. Now, like I've said here, it's a mistake. We could just have one pitch control for all of these. So we have 3 separate graph inputs. We could have just had one graph input for the entire thing. That would have been fine. But as I set up in the prototype, we have 3, so this is just how it is in this instance. So you can see our first one, we're not receiving any pitch shift because it is the idle sound. When the vehicle is stationary, we don't need to pitch shift because we're not doing anything, essentially. As soon as we get to 1000 RPM, that's when we are needing pitch shift, which is why we've connected it in here and in here for our 2000 RPM sound. Then what we're doing is we're going into a print string, and from this multiplier here, where we've multiplied our engine rotation speed by this so that we have 1s and 2s, we have a float to print string conversion, and then this is then going into a print string so that we can essentially see in the top left hand corner of the screen those numbers, and we can see the numbers and then we can hear whether this is working correctly or not. Then we have 2 more set float parameters. As you can see, this is always being attached to the target so that we know which float parameter where that's being set. And the name is 0 CF time, which is, as you should remember, is this one here. So the crossfade time for our idle engine sound. And then we have CF time, which is the crossfade time for everything else. As you can see here, these are both the same graph inputs, so these are being set using this one. And then we have some variables here, which are essentially, they just hold the value 0.25, which is giving us that 250 milliseconds. And then we have 0.5 here, which is giving us that half a second. The reason I'm using variables is so that, let's say I want to set this in multiple places in the code, I can then just grab that variable and I can change that value for the entire code rather than having to go through each individual float parameter and have to change that every time. So hopefully that makes sense why I've done it as a variable. Once we're coming out of these float parameters for the crossfade logic, we're then going into branches, and these branches are helping us determine essentially what should we be hearing in this moment. Should we be hearing the sawtooth wave because the car isn't moving forward, in which case this will be set to 1 and these two will be set to 0. Are we at 1000 RPM or greater, in which case this should be set to 1 and this should be set to 0 and this should be set to 0? Or are we above 2000 RPM, in which case this should be set to 1, this should be set to 0 and this should be set to 0, ultimately determining which of these test tone generators that we're going to hear. And that is essentially the functionality which is going to be in the full engine system. So let's go over how we actually do that. So it's a branch, and the condition of that branch is, are we less than 1, aka are we less than 1000 RPM on the engine rotation speed after it's been multiplied by 0.001. So are we less than 1, and here this is where we have the multiplier 0.001, then we are getting the chaos wheeled vehicle, getting the engine rotation speed and putting that into here. So we have a value coming out of here being multiplied by 0.001. We're asking, are we less than 1? Now if that is true, we are setting these 3 float parameters which relate to the volume graph inputs here. So in this instance, we are less than 1, therefore we want 0 volt to be 1, we want 1 volt to be 0, and we want 2 volt to be 0, which means in this Metasound, we will be hearing this sawtooth wave, but we will not be hearing the sine wave or the square wave, because this will be set to 1, and these two will be set to 0, meaning that the mono mixer is basically got gain 1 and gain 2 at 0, and gain 0, we're actually getting some volume through to the output mono. Now, if we are not less than 1, then it's false. We go into another branch, and then we're essentially querying, are we less than 2? And it's exactly the same thing here. We're getting the vehicle, the chaos wheeled vehicle, getting the engine rotation speed, getting the engine rotation speed, multiplying that by 0.001. Are we less than 2, aka are we less than 2000 RPM? If it's true, then again we are setting these float parameters. We're saying we want 0 volt to be 0 because we don't want to hear the engine idle sound. We want 1 volt to be 1 because we do want to hear that middle one, the one between 1000 RPM and 2000 RPM. And we want 2 volt to be 0 because we do not want to hear the final one, the square wave, because that's for 2000 RPM. Now, if it's false again, that means we must be over 2000 RPM, and this is the final part of our code. We're setting 0 volt to 0, 1 volt to 0, and 2 volt to 1. So, to go over this inside of the Metasound, the sawtooth wave is heard when the engine is idle, when the rotation speed is under 1000. As soon as that rotation speed goes above 1000, we start to hear the sine wave. And as soon as the engine rotation speed goes above 2000, we then start to hear the square wave. And this is ultimately what's going to help us avoid excessive pitch shifting. And it's also what's going to help us crossfade between all of those individual sounds. And this is sort of the concept of the entire thing. We want to be in a situation where, let's say, if we could go out and record an actual real car engine, we could record it at 1000 RPM, 1250 RPM, 1500 RPM, and you could go up the entire RPM range of that car, and then you could have them essentially being crossfaded and minorly pitch shifted in such a way that the player won't even realize it's changing those audio samples, and you get that perfect record and that perfect capture of what that car engine sounds like. Now that we've went over all of that, what we want to do is test it and make sure that it's working correctly. So if I press play now, what we should hear is a sawtooth wave, which is representing our engine idle sound. When I rev up the vehicle and we start getting higher revs, we should start to hear the sine wave. You'll know it's a sine wave because it's a much more pure tone, a lot less harmonically rich. And then when we get above 2000 Hertz, we will start to hear that square tone then. So let's press play. So you can hear there, you can see there on the side of the screen, the top left, it says 0.9. That means 900 Hertz. It's below 1000 Hertz. Therefore, we are hearing the sawtooth wave. If I start driving forward now, you can hear the sine tooth wave there, and you can see in the top corner we're about 1.6, 1.7, 1600, 1700 RPM. If I go above 2000, we get that square wave there. So we know it's working correctly. Now let's go and do a little bit of problem solving just in case you're running into some issues, so that we can try and find out what your issue might be. One way to check that your code is working correctly is by using print strings. So we already have one here, you already seen that. That's essentially taking the engine rotation speed with this multiplier and it's spitting out those values of which are in like 1s and 2s. So that's letting us know that when it should change. So when we see 1 or more, we know we should be hearing a sine wave. When we see 2 or more, we know we should be hearing the square wave. The other thing you can do is you can go to these branches and you can do more print strings to make sure which one should be triggering when. So for instance, you can come off here and you can get a sequence. And from this sequence, we can do a do once. And then out of the do once, we'll then get a print string. Now for this print string, we'll say less than 1 is true. So if I do less 1 true, that's going to let us know that we are less than 1, and you can do the same for this. So when it's false, you'll say less 1 false, and say less 2 true, and less 2 false. And then as you're going up and down the RPM ranges, that'll let you know where you are essentially. So if I press play on this now, what I will do, I'll actually remove this print string just for the time being, otherwise we'll just be bombarded with loads of values. Compile that, save it. Now when I press play, it should say less 1 true, less than 1 true. So you see it there, top left, it blinked on quite quickly and then went away. It said less than 1 true, so that we know that's being triggered correctly. So what I suggest you do is go through your code, and where you think there might be issues, just put a little print string to see if you're getting a execution pulse through. If you're not, then you know that's where the problem lies. And that's it for today. Next episode, we will be going over all of this. This is the entire engine Metasound with the proper wave players being used. And it may look a little bit intimidating, but the bottom line is, if you understood this and understood how that gets working together with this blueprint here, the bottom line is you will be okay with this Metasound here. It's actually much more simpler than it looks. So I'm going to leave it there. Thank you very much for watching. I'll catch you next time.